spray, and I can't remember.
Welcome to the penultimate session of the CONEXS conference. So we've got three really interesting looking talks here. So the first talk of the afternoon session is from Stephen Delhommaye, who's from Sorbonne University, and he's going to talk to us about assessing quantum thermal nuclear fluctuations on multipolar contributions in core level spectroscopy. So take it away, Stephen.
Okay, thank you for the introduction, and also thank you to the organizers for giving me the opportunity to talk. So as I was said, I'm Stephen, and I'm a PhD student at Sorbonne University under the supervision of Delphine Kamal and Guillaume Radke. And in this talk, I will tell you all about, at least all I know about assessing quantum thermal nuclear fluctuations on multipolar contributions in core level spectroscopy. But first, I will give you a brief overview of the theory and methods, the calculation methods that I used in this work. So as many of you, I studied the use of core level spectroscopy techniques to investigate materials. They're called that way, of course, because they involve the excitation of a core level electron towards empty states. So here, using X-rays. And this technique, as I think it was Amélie told us yesterday, they are very interesting because they present a double selectivity, both chemical and orbital. And that means that because each element has its unique core level energies, we can obtain, using these techniques, precise information regarding local structure or electronic properties for specific elements that we choose in the materials. However, the way the information is hidden in the spectra often means that fine analysis requires, for example, ab initio calculations. And in this work, all calculations were done using the Quantum Espresso open source suite of code. And that means we are in a DFT framework, so single particle, pseudo potentials, and a plane wave basis for the wave function expansions. Okay, so how do we model those spectra? We just need to calculate, in fact, their intensity, which is proportional to this kind of golden Fermi rule. That is to say, the transition probability from a ground state that you can see here to a final state, both states being coupled by a transition operator, which depends on which spectroscopy technique we are using, that is to say, which light-matter interaction is at play. Here, the final state is calculating with a core hole, and so the core hole must be isolated in a supercell. And the ground state is just a classic atomic orbital. So in this work, I mainly used two spectroscopy techniques. In fact, I used only two spectroscopy techniques. So first, the well-known X-ray absorption spectroscopy, so where the core excitation is just caused by the absorption of an X-ray photon. And I also used X-ray Raman scattering, also known as non-resonant inelastic, X-ray scattering. It's hard to say. So not to be mistaken with the RIX that we saw yesterday in some talks. Here it's non-resonant, which means we use a higher energy. So here we have two phenomena that are different. So of course, the transition operator involves different quantities. So here we just have the polarization and the wave vector of the incident beam. Whereas here, as it is a scattering process, we have the momentum transfer vector. But the common point of these two is that they can be separated into several terms that are stemming and that are the signature of different transition channels. So I describe them more precisely here. For X-ray absorption, we just have the dipole and quadrupole channel that are ruled by these two specific transition rules. And that means that for this spectroscopy technique, we have access to 1s to p and 1s to d transitions if we are looking at the K edge. For X-ray Raman spectroscopy or scattering, we have access to all these three channels, even though in this work, the quadrupole channel is going to be very weak, so it's actually not going to be here. So we have access to the monopole and dipole channel, that is to say 1s to s transitions and 1s to p transitions. The goal of this study more precisely is to study and model the effects of the thermal vibrations of the nuclei on all these different multipolar contributions. And we're going to see that using two cases. So on one hand, we have the measure of in XRS of the kh of aluminum in corundum, so Al2O3 at room temperature, and it was measured using a high value for the Q vector, so that we had access to both monopole and transition channels. And here we can see the experimental spectra. It was measured at ID20 at ESRF. And on the second case, this time we have in X-ray absorption spectroscopy, so dipole and quadrupole channels. We have the measure of the TI-KH for several temperatures ranging from 6 to almost 700 K. And this time the measure is done on a single crystal as opposed to a powder here, because there was a very specific experimental setup that allowed to measure not only the spectra, but also, and its temperature dependence, but also the temperature dependence of the anisotropy of the 3D states. And we'll come back to that later, but I can already tell you that it caused a profound questioning as to how we should or should not model vibrations when angular dependence is at play. But first thing first, simple results regarding these two cases. So, no, sorry, not results yet. We have to know, I will tell you how to model the vibrations, how at least we modeled all the vibrations effects in the spectra. We used the calculation protocol that is described and developed in Neboza et al. From 2015. And it is placed in a Born-Oppenheimer and quasi-harmonic approximation framework. And so basically, we use this big, scary expression. Actually, scary depends if you like formulas or not, but still it's quite big. But the simple meaning of this is that we can calculate a spectra that includes all the vibration, the thermal vibration effects as an average of a number of single spectrum, all calculated for out of equilibrium configuration of the material. And so here we have just out of equilibrium spectrum for one of those configuration. More concretely and perhaps more precisely, this is a three-step process. First, we perform a phonon calculation on our equilibrium material so that we can get its vibrational properties. A second step consists in the generation of those so-called out of equilibrium configuration, where we just move each atoms from its equilibrium position according both to temperature and the vibrational properties that we calculated beforehand. And the last step is simply, as I told you, to calculate one spectrum for each configuration. So you can see here that each line represents the spectra calculated for one configuration. Here we are looking at the TI-KH, so the titanium KH. And then the last step is just to average those spectra to get the final spectra that is supposed to contain all those vibration effects that we talked about before. So now that we know everything, everything we need to know, we can look at the results. So first, I will present the result for the ALKH in the case of XRS. So we remember that it allows us to check the monopole and the dipole transition channels, that is to say 1s to S transitions and 1s to P transitions. On the left, you have a comparison between calculation and experiment. So experiment is the dotted orange line here. And we have both the calculation using the QHA protocol, so what I described earlier as in dark orange, straight line, and the case for the equilibrium classical configuration, I would say, in a black line. And here it's a little bit hard to see, but I also displayed all the configurations for each of these contribution. And finally, we can see that I shifted vertically the different contributions. So here monopole, dipole, and the sum of both for more clarity. So we can just for now make simple observations, I would say, sorry. First, we can notice that there is a slight shift towards lower energy when we use the protocol of about 0.3 eV. The second thing to notice is that there is a much bigger effect of those vibrations on the dipole contribution. Here we can see that the configurations are very dispersed. It's not the right word, but you get the idea. Compared to the monopole, where the configuration is still quite stacked. So bigger effect on dipole contribution than on monopole contribution. And we can see that the effect on the monopole is just a slight decrease of intensity plus the slight shift toward lower energy. But that is general to all contributions. So just for the contribution, the effect is a slight decrease of this peak, the A peak, at least the monopole contribution to the A peak. And for the dipole part, we can see that there is a big decrease of the B peak, as well as the growth of a dipole contribution to the A peak. We know that the A peak here is supposed to be a signature of 1s to s transitions. And so we're not supposed to see this peak. So we are going to try to somehow explain it. And the projected density of state calculation can help us do just that. So here, this is what I display. So the calculation of projected density of states. Here we just have the kh at equilibrium, so with the monopole and the dipole transition. And we can see that at equilibrium, the dipole does not show any contribution on the A peak. And then below that, you have the absorbing and neighbor aluminum S states and the absorbing and neighbor aluminum P states. And so if we look at the A peak, at the region of the A peak, as I told you just now, there is no contribution, there is no dipole contribution to this peak, which tends to show that it is indeed a signature of just transition to the empty S states. As a matter of fact, if we look at the density of state, there is no P state whatsoever. And so we can deduce that the effect of the vibration is to create a forbidden contribution to the A peak. And we know that it's forbidden because someone mentioned yesterday that when the absorbing site was centrosymmetric, I think it was Francesco, I think, but when the absorbing site is centrosymmetric, local hybridization between P, or let's say between at least absorbing states, is forbidden, but it's not forbidden when it is non-centrosymmetric. Here we have a centrosymmetric aluminum site, and so it's a given, I would say, that we are not seeing any P states here on the signature on the S states. And so the effect of the vibration is by breaking local symmetry to enable this forbidden contribution to appear. So this was globally for the XRS aluminum KH in corundum. Now we can look at the titanium KH in rutile phase of titanium dioxide. So once again, I compare experiment and calculation. So here, maybe I will just move the cameras of everyone so I can see what I'm showing. Okay, so here there is a comparison between a global comparison between all the experiment and the calculation that we performed. So here it's all the contribution at once, so dipole and quadrupole, E1 and E2. And here is just a zoom of the pre-edge region where I separated once again vertically all the contributions. So here we have the E2 contributions times 5 because else it's too small to see anything, and the dipole contribution and the sum of the two, which that part is meant to be compared to the experiment. So once again, we can start by making some simple observations. We can see that the temperature dependence of the spectra is quite well reproduced. And this is even truer, I would say, when we know that using our theoretical framework, when we calculate the spectra, just taking into account thermal expansion, those three spectra are in fact superimposed on each other. There is no change whatsoever. So it's really refreshing to see that we can indeed show such temperature dependency. Oh, sorry, I'm spoiling you. Once again, we can see that there is a different intensity regarding the effect of vibration on dipole and the secondary channel, which is here the quadrupole channel, we can see that the effect on the dipole contribution here is much bigger than the effect on the quadrupole contribution, with the quadrupole almost not changing whatsoever. Whereas on the dipole, we have a big increase of the A1 and A2 peak mainly. So once again, we're going to try to explain that. And once again, our best range is going to be the projected density of states. So once again, I show them to you. Just like for aluminum, here we have the experiment that is compared to the equilibrium case. So the E2 and the E1 contribution at equilibrium, the black line being just the sum of the E1 and E2 contribution. And below that, I show you the respectively the absorbing TI and the neighbor TI P states, and then the absorbing TI and the neighbor TI 3D states. And so using this projected density of states, we can kind of tell what 3D state is represented in each of these peaks. So we can assign each peaks according to some transition to 3D state. So if we focus first on the A1 peak, we can see first that there is only a quadrupolar contribution to the spectra. The dipole is 0. And so we know that this peak is related to a direct transition to 3D state, so Ni2 contribution. And indeed, when we look at the density of state, we only see that the 3D T2G state, and so we know that the A1 peak, at least at equilibrium, is a signature of a direct transition from 1s to the 3D T2G of the absorbing titanium. This is for peak A1. I would also like to mention that just like aluminum, you can see here this, the titanium site. It is centrosymmetric, and so we do not expect any local mixing between the P and S states. And it can be seen here. You can see there is no P states here whatsoever, at least at equilibrium. So we talked about the E1 peak. We can talk in the same way about the A2 peak. So if we look at the spectra, we can see that there is both an E2 and E1 contributions, and so we know that this peak will involve both the absorbing P and the absorbing 3D states. And when we look at the density of state, we can see that there is both absorbing and neighbor 3D states. And so we know that this peak is related to both a direct transition towards the 3D EG states of titanium by a classical 1s to 3D E2 transition, but it is also a sign of the 3D T2G, this time of the neighbor, via non-local mixing. So in fact, there is a transition towards the absorbing P states that are mixed with the neighbor titanium 3D 2G states, 3D T2G states, sorry. And by doing the same work for the third peak, we can see that it is purely a signature of the 3D EG states of the neighboring titanium atom via mixing with the absorbing titanium P states. And so we have this this well-known, now it is relatively well-known, this separation between transition meaning for each peak. And if we had vibrations, kind of like before with aluminum, because we know that it adds Ni1 contribution to peaks that are supposed to represent the 3D states of the absorbing atom, we know that the vibration caused the breaking of the local symmetry of the site, which allowed the forbidden local hybridization between the absorbing P and the states atom, which is why it creates this forbidden contribution here and allows the peak to grow as temperature grow. And so looking at these two cases, so the ALKH and the TIKH, we could get a brief kind of a general overview of the effect of vibration. But if you remember what I told you before, for titanium dioxide, we also have the measure of the anisotropy of the state, so which is this signal here, which has been multiplied by 10 to, so with that we can know what is happening compared to the general spectra in the pre-edge region. And the experimental setup was made so, in fact, this signal that is measured as a difference between a signal giving the maximum A1 intensity and the minimum A1 intensity given the symmetry of TiO2, which is D4H, it should only come from the E2 contribution. But when we try with our method to simulate this signal, here is what we get. So here is the E2 contribution, here is the E1 contribution. And as you can see, there is a big problem that I can help you figure out by surrounding it in big flashy red color. And here the problem is that even if the E2 signal resembles quite well I don't have much time, I will go fast. The experimental signal, we have a non-zero E1 part that is completely unexpected. And so either we have a miracle on our end or an unseen problem. The first idea is to think that it's a convergence problem, because as a matter of fact, all the spectra we get, their convergence is the function of the number of configuration that is used. So we can check it. Here is the result we get for 40 configuration, for 80, for 120, etc., until 200. And here we're starting to get hope because the E1 signal is starting to get to zero little by little. But if we add more configuration, as the SATCAT indicates here, we're not very happy because it seems to be converging to a non-zero signal. And as a matter of fact, when we add more configuration and more, the signal indeed converges to a non-zero contribution to a non-zero signal for the E1 contribution, which makes the SATCAT go away in dismay. And so we have another problem, and it turns out that this problem, in fact, is a symmetry problem. And I will go very fast on this part, and maybe you can ask me questions to explain. But according to Christian Bruder, here's what the cross-section should look like in our specific experimental setup. And you see that when epsilon varies in this plane, it is always the same thing. So in fact, the E1 contribution must be zero here. But in our general case, you see that we have additional terms here that are added and that are caused by the loss of symmetry that is present on all configurations. And so the loss of symmetry that helped us before, like reproduce temperature dependency and subtle effects on the spectra that are observed experimentally, here becomes a problem to reproduce the angular dependence. And we know that TiO2, even if temperature increases, it stays TiO2, and so it must have the same symmetry. And in fact, we showed it, because in this study, we managed to show this expression as long as S is a symmetry operation of the crystal point group. And what this means in English is that very simply, the average cross-section that we calculate must have the same symmetry properties, as the cross-section calculated for the D4H symmetry, which is the symmetry of the TiO2 rutile crystal. And so the goal from here is to recover the symmetry by adding and subtracting some terms. But you can ask me this and some questions because I'm overstepping a little, sorry. So here is an example you can ask me later. I can explain you if you want, like in networking or whatever, but the idea is to use a well-chosen linear combination, of orientations so that we can get rid of the unwanted term. And in the end, as you can see, when we use this, we can recover the zero contribution, to the spectra while keeping the same conclusions we had before. So we managed to at once keep the effects given by the loss of symmetry and correct the problem that they also bring. And so for a rapid conclusion, in this study, we could get a global overview of the effects that the thermal vibration have on the different multipolar contribution to this kind of spectra, and that the main effect was on the dipole part by enable local mixing of NTP and is or D states, whether we're looking at XAS or XRS. And we also devised a method based on group theory that allows us to recover the symmetry that is lost when we use atomic configurations. And it should be noted that this general technique is not just usable in our case. As soon as you're using snapshots of your material and you're trying to look at some angular dependence, you can use this general method to recover it without losing the previous result you obtained. And finally, this work is gonna soon be published in this paper that you can see here. And thank you for your attention. Sorry for overstepping. There was a lot of things to say. And thank you, I guess, to my team, to everyone. Thank you, everyone. And sorry for overstepping.
Okay, thanks very much. The really interesting talk, and surprising the large effect of that temperature has on that range. It's really interesting. In the interest of time, we probably should move on. But there is the Q&A section. So if you want to ask a question in there, then I'm sure Stephen will be happy to, or the chat, and Stephen will be happy to answer it. While the next talk is going on. So no, thanks very much.
Again.
Oh, don't worry. No, thanks very much for an interesting talk.
Thank you.
Okay, so
I will keep the sharing my place. There we go.
Right, thank you. So we're now on to our second talk, and this is from Kamal Chinnathambi from Stockholm University. And he's going to be talking about hydrogen bond arrangement on water in TiO2 surface from core level binding energies. Whenever you're ready, Kamal, you can take it away.
Yeah, just a minute.
Yeah, no worries. Okay, so sometimes as you're not on full screen mode, you're not. So sometimes you have to put it on full screen mode and then share the screen.
Okay.
Just try that.
Yeah. Still. See my screen again?
It's still on presenter view. So if you, there we go. If you put it on full screen mode now and then start sharing.
Yeah,
brilliant.
Yeah. Just a minute. Give me a second.
Yeah, no worries.
Now I think you should be able to see it.
Perfect. That looks great. Right, over to you, Kamal. Brilliant.
Yeah, thank you. Thanks for the introduction, and also thanks for this opportunity. I'm Kamal. I'm a postdoc at the Department of Physics, Stockholm University. I work in a group of Professor Michael Odelius. I hope I'm audible to everyone. And also, I'm from India. I work in Raja Ramanna Center for Advanced Technology, which is my parent institute. Today, I will talk about the hydrogen bonding configuration of water molecules on titanium oxide 110 surface. So these are my outline of my talk. I briefly mentioned the motivation, and then I'll go to the orbital representation of XPS. Then I'll come to how to model the spectroscopy, and then move on to the results on water molecules on titanium oxide surface. Finally, I'll give a summary of my work. Okay. So we all know that the titanium oxide is a very important oxide material which has been used in several fields. So among the titanium oxide, rutile is a very well known, and also it's the most abundant. It's the titanium oxide in rutile 110 is a prototype oxide surface which has been used for several, which has been used as for studying several model studies for the absorptions. So it is a very important surface, and also it has been very well studied. In spite of that, the molecular mechanism of the water absorption, especially the wetting of wetting, how the wetting process taking place on titanium oxide surface is not very clearly understood until now. So the aim of our work is to identify the molecular configurations involved in the wetting process, and then for that we need to understand the molecular mechanism. Once we understand the molecular configuration, we can use that mechanism to understand the wetting process. So for this purpose, we use both experiment for XPS and also the theoretical calculation from DFT. So I'm not an experiment, I'm from the DFT side. So basically, I'll start from the computational side. So these are the people involved in the work. Michael Odelius from the Stockholm University, and then Nader is a master's student, and Natalia from the KTH, Royal Institute of Technology, and also Anders is the main person in the experiment and his postdoc, previous postdoc, David, and also several other people involved in the experiments. So I will start from the computational side. So we use a density functional theory, as I mentioned, using the CP2K code. These are the computational parameters used in our calculations. This is for the geometry optimization, and also we use all electron method for the XPS simulation using the GAPW method. So we use the slab model that I think most of the people know about the slab model. It is not the three-dimensional periodicity. We break the three-dimensional periodicity in one direction. So for that purpose, we add a vacuum layer in one of the direction, so that when you apply the periodic boundary condition, the material is repeated in two directions, X and Y, but in the perpendicular direction, we have a vacuum. So that it creates two surfaces, top and bottom, about top and bottom surface of this slab, so on which we absorb the molecules. So we use a symmetric slab, meaning that the top and the bottom side, they are mirror image. So this is the slab we use for our calculation. You can look at the top and then side view of the slabs. So before going to that, I want to give briefly. I want to briefly mention what is this surface. So titanium oxide 111 surface looks like that. This is a slab. This slab contains 7 tri-layers of titanium oxide. So it contains 21 atomic layers. So you can see that why, and also we know that whenever you create a surface, the surface unit cell can be different from the bulk unit cell. So in order to define the surface unit cell, you need 2 parameters. One is the length and then another one is the breadth. You can say that if the angles are 90 degrees. So in our case, I choose 2 cross 5. This is one of the direction. A direction, we have a 2 unit cell. You can see the 2 repetitions. In the B direction, we have a 5 repetition, which makes 2 by 5. 2 by 5 as a surface. So in the 2 by 5 surface supercells, we have a 20 titanium oxide, and then remaining 40 oxygen atoms. So on the top surface, you can see that the red arrow indicates this is a top oxygen atoms belongs to the titanium oxide, which is a doubly coordinated. But we also have a titanium, which is 5 coordinated. So these titanium 5 coordinators act as adsorption sites for the water molecules. So if you compare with the bulk, so their coordinations are 3 and 6. Here bridge and then the titanium 5. Okay, so this part I think that including the previous talk, I don't need to spend more time on it because everybody talks about everybody knows about the X-ray spectroscopy. Just I wanted to tell only one thing. In the previous presentation also it has been mentioned that we have a ground states that all the levels below the Fermi level have been completely filled, above which empty. But when you apply the X-rays, either we can have a XPS where the core electrons are ejected out of the system, or the core electrons transfer from the core to the unoccupied state. In both cases, we have a core hole present in the systems. Once you have a core hole present in the system, all the other occupied orbitals also needs to be relaxed if you want to give a correct description for the final state. So that is very important. So that the orbitals, whatever we are representing in this ground state and then the excited states, they can be different because of the orbital relaxation. That we need to take into the account. That is very important if you want to give a correct description of the electronic structure of the excited state. So how do we do it? So the simplest starting point for a theory is a Hartree-Fock method. I will not go into the details, but Hartree-Fock is simple Slater determinants where you expand the many body wave function in terms of single particle wave function, which are pi 1, pi 2, pi 3. So ultimately, when we solve this second equation, Fock equations, you will end up with calculating, end up with this pi i's and then epsilon I. This is what we do in any quantum mechanical problems. We get the eigenvalues and then eigenvalues and then eigenfunctions. So once you have this from the Hartree-Fock calculations using a Koopman's theorem. It says that all these eigenvalues of this single particle orbitals, they correspond to the ionization potential. That meaning it is the energy required to remove an electron from this particular orbitals is equal to that of this one. So if you want to calculate the XPS, what we need is the binding energy of an electron from a particular level. So we can use this one. But the major problem is that we are doing a simple ground state calculations where there is no core hole present in our systems. As I mentioned in the previous slide, we need to incorporate the core holes in order to give the correct description. That is a major approximation involved in this. Another thing is that artifact, we know that by using a slated determinants, we incorporate the exchange or the Pauli exclusion principle in a correct manner, but it misses the correlations. So how to go about it? And also for a periodic systems, especially the system what I'm talking about, the slab model, which has such a big size, typically around 450 atoms in a supercells, you need to go for a much more simpler computational methods. So we choose DFT because it's a very good scaling. So in DFT, instead of going into the orbitals, using the orbitals as a orbital to calculate the energy, what we do is that we perform two separate calculations. One is with the n electron, another one is the n-1 electrons. So you can see that these two represent the initial and then final state of it. So, and also you can that the energy levels can be relaxed because in both cases we completely optimize the orbitals. So that by intrinsically the presence of core hole, the relaxation effect has been taken care in the second calculation. So what we do is to simply take the difference between the energy difference between these two n and then n-1 system. That gives you the ionization potential that is equivalent to the binding energy. But also, as I said in the previous, we missed the correlation. But in DFT, what we do is DFT by principle, it includes exchange and also correlation included in the DFT calculation. But everybody knows that there is still we don't know except the homogeneous electron gas systems. We need to go for an approximation for something called exchange correlation functional. We use the standard GGA, that is PBE, and also we went for PB0, which is hybrid calculations. So this is the method we use for the calculation. Now I come back to, first I will go to the experimental results. So this has been performed by Anders from the Uppsala University. So they performed the experiments on the titanium oxide and the water molecules are absorbed on the titanium oxide 110 surface. You can see that in the first figure. So this is the atomic model, atom ball and stick model for that. So first, clearly we can see that we have three peaks. So in the measurement, so the first one is the most intense peak is the correspond to the oxygen in the titanium, and the next two species correspond to the OD, and that's OH, and also the water molecules. One is a neutral, and another one is a dissociated species. So the dissociated species is very close to the titanium, and then the water molecules, the signal correspond to the neutral molecules far away from the main titanium oxide fields. So the most important thing is that from using this XPS technique, the experimentalist is able to distinguish the peaks between the OD and the water molecules, so that the XPS can be used to differentiate both the molecular and the dissociated molecules. And also they also perform the experiment with the different temperatures. You can also see that when you go to the different temperature, you can also see that there is also a shift in the water molecule peak. So this shift can be used to understand the structural you can use this to get the structural information from the experiment. That is one thing. And also they perform the growth using at three different temperatures. They perform the uptake of this water molecules. So you can see that in the very low temperature, 97 Kelvin, there is no limit for absorption because the ice at 97 degrees under the ultraviolet vacuum is quite stable. So when you put this on the surface, it is quite stable. diffuse and then spread out. So there is no limit to it. But when you come to the 160 degree and then 210 Kelvin, there is a saturation. After sometimes they get saturated. So the next one is the line go to the from using these two signals, they could be able to obtain the ratio between the neutral molecules and also the dissociated. But if you can see that they also depends on the temperature. So you can see that at the very high temperature, among these three temperatures, the highest temperature, that is the 210 Kelvin, they can see that the more dissociation happening at the 210 temperatures. So the dissociation depends on the temperature. This is one can obviously expect this one. But the most important results from the experiment is this slide. So this slide contains the binding energy information. Instead of working the absolute number, they take the difference between the titanium oxide, the oxygen from the titanium oxide, and also the water molecules. There is a difference between these two. So you can see that these three temperature traces a different path. There is also here some overlapping region. So the first one, if you go from the lower temperatures, the 97 Kelvin, so it starts from the very high value for the binding energy difference, and then it has monotonically keeps on going down. So it's obvious that when the molecules are isolated, when they are when you pour, they are separated. But once you pour more and more, once the more aggregate forms, so it is very well reported that whenever there is a network forms between the water molecules, then the binding energy started to decrease. That is what happening with the 97 Kelvin. It keeps reducing before even reaching to the one monolayer. You can see that they are continuously keep on reducing. Okay, if you look at the 160 degree Kelvin, it also starts from the high values and then it's coming down, and then almost it becomes saturates, and then it reaches at one monolayer certain values, that's around 3.7 or something like that, then again decreases. The decrease in the after a monolayer is very well expected, because once one layer is formed, then you form a layer network. You are pouring the water on top of the first layer, then there is a more network is forming. So it is again expected that the binding energy values will decreases. But the most important question is that when you go to the 210 Kelvin, it starts with the pretty low values, and also that these values are when you start growing, the values are not decreasing. It is initially decreases, and after it goes to the value which is very low compared to the other two people. One, and then when you go to the one monolayer, it started increasing. But this part is not very well, it's not very obvious, because once you pour more and more water molecules, the extended network should start, then it should keep on decreasing from that. Okay, either so this part is not at all. Why this for the lower coverages, the value of the binding energy values are quite low. That is not clear. Okay, so this is what one of the main important motivation from the theory side to explain why these things are happening. Okay, this part I already mentioned. So we need to ask that why it is so lower. So before that, do you have any kind of clue from the experiment why this particular case is different? If you remember the previous slide, the only major difference between the 210 degree and another temperature is that in this case we have a more degree of dissociation for the 210 degree. So that may be the one of the reason for that. That's what the information we got from the experiments that we trying to use it in our calculations. So what we do is that we have a super slabs on the 2x5 surfaces on which we absorb the water molecules in different possible combinations with a different coverage. Here I am showing an example for the 30% coverage. We have a 10 absorption site. Among the 3 of them are absorbed. There are several possible ways you can put the molecules. Okay, so these are the some of the minimum energy structures. So then what we do is that in order to track all kind of this configuration, what we use a notation for that, how the molecules each molecules donates the hydrogen bonding. So that the arrow indicates that this first molecule donates a hydrogen bonding to the next one. This one donates the molecule to another one. We're trying to keep it very simple within the 3 notation, because So if we go to the very larger, the linear chain will be formed. Instead, we could work around within the very simple pictures where we can say that nearest neighbor interaction may be quite good enough. So that's why we retain these notations. Okay, so the using after absorption, we perform the geometry optimization, and then we calculate the absorption energies. So this is the formula we used for calculating the absorption energies. Once we have the absorption energy, these are so in this slide I'm showing what are the different possible combination we used it. I will come to the color coding, why I'm using the different colors for the molecules. Okay, so we used a total of around 15 configurations, and then there are around 60 molecules in the system. For each molecules, we perform the calculations with the oxygen having 1s electron removed from that shell. So we have a several calculation, and then using this one with the ground state calculation, we subtract the energy so that we can calculate the binding energy from this. Okay, so these are the trade for the absorption energies. The first most important thing is that we find that so whenever you have the dissociated molecule as an acceptor, so we always see that in the lower coverage we see that is lower in energy. So this is again consistent with our experimental results, where we see that when you go to the lower coverages, when you have a dissociation is more. So somehow we could able to relate between this the lower binding energy of the dissociated molecule as an acceptor in comparison with the experimental results. That is a very good connection. First, we got it between the experiment and theory. Okay, when you go to the higher coverages, we see that the linear chains will be formed. Then in that case, only the molecular species is favorable in energy. That is also again consistent with this, because when you go to the higher coverages, the ratios keep on increasing, meaning that the degree of dissociation is keep on reducing it. Okay, so this one is energetically the trade with the ratio is consistent. Then again, as a reminder, how we do a calculation, I'm trying to calculate the two difference in energy between the N and then N minus 1 electron system, where the 1 electron has been removed from the 1s, oxygen 1s. Okay, so these are the before going into the details. So what I have done is first I segregate all the classes, what are the species. So then at the look at the energetic. The first most important is that we can see that there is a bunching of all the water molecule signals, whatever we get it from our signal, and also they are very much separated from the dissociated species. So there is a good difference between them. Okay, another one is that they are also difference between the water dissociated molecules and the titanium oxide, oxygen from the titanium oxide. This is exactly the trend what we see from the first slide of the experiments. So that is good. So we clearly see that even from the theory, we could distinguish between these two species, and the order is maintained as that of the experiment. Another important thing is that there are two possible hydroxyl groups happens. One is the water molecule, what you are absorption, that OH. The one hydrogen is dissociated from the water molecule, it also goes and then stick to the bridge site. They will also give a signal. These two are, you cannot distinguish from the experiment. We are also seeing that they are in the same energy range. So far, so good. So our results, and then they are very much consistent. So we wanted to go for the further information. We all know that again, as I was telling, there is also difference in the binding energy of the neutral molecules. That gives a signal, that gives a structural information that we wanted to dig it out so that we can use that signal for the experimentals, explaining the experimental results. So what we use that, as I mentioned earlier, we use a simplest picture where I have a molecular water molecules, neutral molecules, where I'm getting a signal. It has two neighbors. Okay, one is X, another one is Y. But this X, Y can be either it can be empty, or it can be again another molecular species, or it can be dissociated. These are the three possibilities. It can happen. And also you remember that in 2x5 structure, we have a linear chain formed. Okay, so this is a very simple pictures. Once you have it, then you can classify them into the different ways. The most important thing is that this table, we got it for the all different possibilities. then we can see that the grouping of the binding energy difference between the water molecules and the titanium oxide, they grouped into 3 different classes. These are the classes. So it strongly depends on the Y, which is the acceptor. It hardly depends on the X. Then it is not playing any role in here at all. Okay, so using this, we can clearly see that there are different classes. The most important thing is that whenever you have a dissociated molecule as an acceptor, then you have a very low binding energy. This explains so these are the, now you can see that why there are color coding, because they correspond to the different classes in the, these molecules correspond to the different classes depending upon their neighbors. So now I will come to the experiment. So why we are getting this lower value? Because at the lower coverages, we are having the dissociation, high degree of dissociation at 210 degree is most probable one. That is what we see from the calculations, the absorption energy calculation. And also once you have the more dissociated molecules, that dissociated molecule as an adsorptor to the any neutral molecule will give you a very, very low binding energy. That explains that at 210 degree, we have a more cases of MD like dimers or trimer like neutral dimer dissociated, then neutral dissociated, this kind of combinations there. But only important thing is that you should have a D as a acceptor. Once you have that, then you will get this kind of signal. So we know that what kind of the molecular species involved in the initial stage of the growth. So everybody knows that the DFT we always use an approximations. So the people always say that is it all the numbers, whatever all the values we are getting is it only for true for this number, or do we have any influence of the exchange correlation function? We also done the calculation with the hybrid functional, and then we check that these results are very much consistent. So we are happy with it. Then all these results have been published in a URL. So with this, I will come to the end of my talk. So from our calculation, we find that whenever we have a dissociated molecule as an acceptor to the hydrogen bonding, we have an energetically favorable situation, especially in the lower coverages. So using our structural model, we could able to classify 3 different classes. So based on the acceptors, so we could able to explain the lower coverage at 210 degree. There is a very lower values of binding energy. So that we can use it because it contains a lot of dimer or trimers from the class 3, which has a dissociated molecules. So ultimately, I would like to say that this last 5. So using this technique, whatever we propose, they are more in general. It's nothing too specific about this particular system. So what we wanted to say is that XPS and then DFT based this kind of calculations can be used to develop a microscopic understanding of the any molecular surface system. So with this, I'd like to thank all my collaborators. Special thanks to Michael and Fernandez for their help in this work, because they put us, so they were so much helpful for throughout this work. And also I would like to thank the Sneak Computers for the computational facility and also the service. Thank you all for your attention.
Okay, thanks very much, Kamal. Really interesting talk. In the interest of time, I think if we do like we did for Stephen, if people ask questions in the Q&A or in the chat, then I'm sure Kamal will be happy to answer them afterwards. Brilliant. Thanks very much for a great.
Yeah.
The last talk for the session, and it's Martina Fracchia from the University of Pavia. And she's going to be talking to us today about understanding solid gas reaction mechanisms by operando soft X-ray absorption at ambient pressure. So
okay.
When you're ready, Martina, take it away.
Thank you very much. I hope you can see my screen. Okay. So first of all, I would like to thank the organizing committee for this very nice opportunity. Today, I will talk about the 2 operando soft X-ray absorption spectroscopy experiments that we carried out at ambient pressure to study solid gas reaction mechanism. So solid gas reaction mechanisms are at the basis of heterogeneous catalysis and many industrial processes. And in the last years, it has emerged the need to find operando and in situ techniques to interrogate the mechanism of new catalysts. So the ideal technique in principle should satisfy two main requests. The first is the surface sensitivity, because of course the active sites are located at the surface, and then also the possibility to work at ambient pressure. And this is not really and this is not trivial because many of the techniques which are currently used, for example, XPS, which is among the most used techniques in this sense, works at pressures which are quite far from ambient. And this is the so-called pressure gap, and new ways must be found to overcome this pressure gap. Regarding X-ray absorption spectroscopy, hard X-rays have been employed a lot in this sense. So XAS with hard X-rays is now consolidated, and it's very versatile, and almost all the experimental conditions can be reached to simulate realistic working conditions. The same cannot be said for soft X-rays. So these X-rays have an energy which is lower than 1000 electron volts. So they have a very low penetration depth, and usually they have been used for surface science experiments and under high vacuum. However, it's also possible to acquire operando X-ray absorption spectroscopy with soft X-rays at ambient pressure and using total electron yield as the acquisition mode. So this is quite advantageous because this gives the possibility to be surface sensitive. As I said, that there's the possibility to work at ambient pressure, and also the K edges of light elements such as carbon, oxygen, and lithium, and also the L edges of the first row transition metals lie in this range. So this technique can be really informative and can be really a powerful tool to investigate heterocatalysis. As the other side of the coin, we should say that this kind of experiment can be a little more challenging with respect to conventional XAS experiments, and also there is the need to use a specific experimental apparatus. The reaction cell that we used is installed at the APE high energy beamline, which is at the Italian synchrotron radiation facility, Elettra, it's called. This is the scheme of the cell. So here we have the sample, and then we have a membrane, which is a silicon nitride membrane, which separates the inner part of the cell, which is at ambient pressure, with the outer part of the cell, which is kept under vacuum. Here we have also the gas flux. Helium is usually used as a carrier because it facilitates the total electron yield acquisition. And then the drain current is measured from the sample. So in this presentation, I will show two main experiments that we carried out with this technique. The first one is this experiment to study the reactivity of hydroxylated tin dioxide nanoparticles towards reducing gases. So first of all, we synthesized our nanoparticles using a simple precipitation method. We checked the purity with the X-ray diffraction. We could see the cassiterite reflections only. We also did a previous characterization with thermogravimetric analysis. So this is quite important, as we will see in the next slides. So you can see that below 100 degrees, we have this initial loss of weight loss, which is due to the loss of physisorbed water. And then we have above 360 degrees, the loss this time of chemisorbed water. This region here is flat, and that's exactly where we measured. So that's the region that we chose for our measurements. So here we still have hydroxide ions, which are ubiquitous in the surface, kind of oxides, but we have already lost all the physisorbed water. So first of all, we did a treatment of the sample. This was done until 360 degrees in helium to remove all the physisorbed water and also for cleaning of the sample. And then as a first case, we decided to flux hydrogen. And we monitored both the oxygen K edge and the tin M4 and 5 edges. So we could monitor both what happens to the surface of the sample, because we monitor tin, and then we also monitor what happens to the products, because most of the products which are expected to form contain oxygen, so they are visible at the oxygen K edge. So this is what happens if we flux hydrogen. This is the spectrum at the beginning, and this is compatible with a conventional spectrum that can be acquired in high vacuum. So if we increase the temperature and if we start to flux hydrogen, at a certain point you see the appearance of these three peaks here. So these three peaks can be attributed to water in the gas phase. You can see here the spectrum of water at the oxygen K edge, and these are some reference spectra, such as carbon dioxide, carbon monoxide, and water that we acquired in the experiment. So at a certain point, we see the appearance of water in the gas phase. Then water disappears by raising the temperature. And this is because we have saturated the active site in the surface. If we see what happens to tin, at first we have these spectrum and the tin M4 and 5 edges, so typical of tin dioxide. If we flux hydrogen, then there is the appearance of this peak. And this peak can be attributed to tin 2 oxide. So you can see here the reference spectrum of tin 2 oxide. So basically what we are observing is this reaction. So we are observing the formation of water in the gas phase together with the reduction of tin 4 to tin 2. So this of course was expected, and also maybe it's not very exciting, but it tells us that this technique works and that we were sensitive to the surface as well as to the gas products. So at this point, we decided to flux other hydrocarbons. We fluxed methane and then propylene. So with methane, you can see that while increasing the temperature, these three peaks again appear. So this is, of course, in lower quantity with respect to before, because the reactivity is lower for methane with respect to hydrogen, but still we observe the formation of water in the gas. If we look at tin, again, we see the appearance of this peak, so we see the formation of tin 2. The situation is quite analogous also for propylene. And indeed, you can see if we increase the temperature, again, the appearance of these three peaks. This time, these peaks are more visible with respect to methane, and that's also expected because we have a higher reactivity for an unsaturated hydrocarbon. Also, in this case, if we look at tin, we have the formation of tin 2. So this is quite surprising because we observe water in the gas phase, but we never observe some carbon species. For example, we do not observe methanol or formic acid or carbon monoxide. So we only see the appearance of water, at least in this range of temperatures that we investigated. We also could calculate the duration of the quantity, the thickness of the tin oxide layer, which is formed at the surface. And this quantity is about 0.5, both for methane and for propylene. They are quite the same, even if the reactivity of propylene is higher, just because we fluxed methane for more time. So that's why we have the same thickness in the end of tin oxide. But you can see that we are really sensitive to the immediate surface of the sample. So at this point, we wanted to compare our experimental results with some theoretical calculation. So we compared with density functional theory we thought about the 3 different scenarios that can happen. So the first is with a total coverage of hydroxyl ions. So what can happen is that methane we did all the calculation with methane, and also supposing this 110 crystallographic phase, and this was done for kind of simplicity in the calculations. So as a first case, methane can be absorbed, so physically absorbed onto hydroxyl covered tin dioxide. And then we can have the formation of absorbed methanol. And as you can see, it is more favorable from the energetic point of view in this sense to remove water in the gas phase with respect to methanol in the gas phase. So a higher temperature is needed to remove methanol with respect to water. Also investigated another scenario, which is probably it's more probable to happen with respect to our experimental results. So in this case, we suppose to have not a total coverage of hydroxyl ions, but just one tin site, which is free from the hydroxide ion. And in this case, methane can be absorbed on this tin site and cause the formation of methyl-like or methoxy-like species. And these species that are formed are very stable, so their formation is quite exothermic. And also the formation of these species leads both to the formation of water in phase, as well as to the reduction of tin from tin 4 to tin 2, as we actually observe. So we can have this kind of mechanism. So this is a very naive scheme, let's say, but what can happen and what probably happens is that these gases react with the sulfur hydroxide groups to produce water, and they directly release the electrons that localized on the tin sites, leading to the reduction of tin. So actually we saw that hydroxide groups are maybe more important than expected and should be taken in consideration when considering this kind of reactions involving oxides. So this was the first pilot experiment that we did about solid-gas interaction. The second scientific case that I will show you regards more an actual catalytic reaction. And in particular, we studied high entropy oxides as a catalyst for the carbon monoxide oxidation reaction. So these high entropy oxides, so just let me give you a small overview because maybe they are quite new to you. So these oxides are actually a very class of materials which have been presented quite recently in 2015. So the idea comes from the high entropy alloys. So what you do is you mix at least 5 different oxides in equimolar ratio. And if you heat them up, this results into a single phase structure. So this is the material we explored, and also it's the first pioneering system that was explored. It has a single phase rock salt structure, and the possibility to stabilize this single phase is due to the large value of the configurational entropy, which is particularly high in case of 5 cations oxides. And let me say, this kind of material is also quite, it gives quite a lot of satisfaction from a spectroscopist's point of view, because, and especially for XAS, because you can monitor all these edges simultaneously in the same experiment, which is quite nice. Okay, so these oxides are actually being investigated. There's still a lot to understand about some fundamental science, and also scientists are trying to stabilize these high entropy oxides in different crystallographic structures. And they have already found a lot of applications, for example, regarding electrochemical energy production and storage, and also regarding catalysis. So we study this material as a catalyst, as I said, for carbon monoxide oxidation, so for this kind of reaction. We monitored the L edges of copper, cobalt, and nickel to study the mechanism of this reaction. We also acquired at the same time gas chromatography, so we could also monitor the formation of carbon dioxide. And you can see that the maximum of carbon dioxide is formed at 250 degrees. So let's take a look at copper at first. So this is the spectrum of copper, the yellow one. This is under helium. And this shape is typical of copper 2 oxide. What happens if we flux the stoichiometric mixture, so carbon monoxide and oxygen, at 250 degrees? You can see that this peak appears. And this peak is due to the formation of copper 1 oxide. So it's due to the formation of copper 1 sites. What happens if we flux oxygen? This peak disappears. If we flux just carbon monoxide, this peak appears again, and it's also larger in intensity. So it's quite easy to understand what happens in this case, because we have carbon monoxide, which is absorbed into the surface, and this leads to a charge transfer, so to the formation of copper 1. When carbon dioxide leaves the surface, then we again have the formation of copper 2. So copper is the metal which is involved in this catalytic reaction. Actually, the fact that we observe this peak means that the reduction is faster with respect to the oxidation. And this can be explained because an additional energy should be added to remove carbon dioxide from the surface. So this is what happens for copper. If we look at cobalt and nickel, nothing happens. So in all the cases that we considered before, you can see we still have the same spectral shape. So this means that nickel and cobalt just act as spectators, so they do not have any kind of role in this kind of reaction. So at this point, two main things should be taken into consideration. The first one is that this high entropy oxide is active towards the reaction, but none of the parent oxide are active in this reaction. So for example, if you take a copper 2 oxide and you flux carbon monoxide, this is immediately reduced to copper 1 oxide. You can see, here, this is this yellow spectrum. So if we flux carbon monoxide on copper 2 oxide, we have a massive formation of copper 1 oxide. So this means that the configurational entropy really is able to stabilize these sites. So it's able to stabilize the copper 2 active sites. And indeed, we did a sort of stability test in this sense, because we fluxed the carbon monoxide on this high entropy oxide for 1 hour and at a temperature of 235 degrees. And you can see we never form so much copper 1. I mean, the copper 1 formation is always limited to less than 10%. So the configurational entropy really has a role in this stabilization, and it can also offer a new paradigm and can be also used in other kind of materials to try to stabilize exotic or maybe more unusual oxidation states. Okay, so I come to the conclusion of my talk. We successfully carried out operando soft X-ray absorption spectroscopy experiment at ambient pressure, and I think that this can be considered as a technique, as a powerful tool for the investigation of catalytic reactions. And in particular, we studied the interaction between thin dioxide nanoparticles and hydrocarbons. So we could observe the interesting role of hydroxyl ions. And then we also studied the mechanism of carbon monoxide oxidation on this high entropy oxide, and we saw the role of copper and a nice and important role of the configurational entropy. So at this point, I just want to thank all the people who contributed to this work, especially my supervisor from University of Pavia and all the staff from the APE High Energy Beamline. And of course, I would like to thank you for your kind attention.
Hello, thank you very much for a really interesting talk. So we've got time for a couple of questions. So again, either in the Q&A section or in the chat, or if you're a panelist, you can turn off your mic. Oh, Sophia has a question.
Yeah, Victor has his hand up.
Okay. So Sophia, if you still go first, and then Victor.
Hi, thanks for this.
So very quick, Martina. I just wanted to know, in the high entropy solid, as you say, is the the ideal system for a spectroscopy person doing XAS. You said that you see the copper changing, but you don't see any changes in cobalt or nickel. I think you said. Mm-hmm. What about the other? Yeah. You have zinc as well.
Sorry, I thought you have.
So I mean the other that you had not mentioned. Sorry.
Oh yeah, zinc, for example. Yeah, we studied also zinc. I did not show the spectra because we did it in another experiment later. And in this case, we do not observe any effect. So we studied zinc. We did not study magnesium because actually we do not expect that effect on magnesium, and also not easy to reach from the spectroscopic point of view. But yeah, zinc was studied and we did not see any change.
And you also did the thing with soft-XAS, also in the same setup.
Yeah, exactly. The same setup, yes.
Thanks.
Thank you.
Now Victor's question.
Hi, thank you for this nice talk. I just was wondering, what was the choice of temperature? Like, why did you choose those temperatures to measure with? Because I think if you go even higher, you are able to induce more changes, like breaking the dangling bond saturation and saturate them with compounds from the gas that you use.
Yeah.
Yeah.
Yes, you are right in this sense, because we were limited by the experimental possibility. Because the cell actually, so the experimental cell only could reach basically 350, 360 degrees. Now we have made some new adjustments, and it can reach about 400 degrees, but it's not that easy to go further in temperature.
Mm-hmm. Okay, thanks. Good.
Thank you.